Hooke's law says that if you have a spring, okay, all springs kind of have a natural length. Like if you just leave it and don't compress it and don't pull it, it has a natural length. The force to pull it or to push it past its natural length is a linear function given by force is equal to some constant that would be unique for each spring times x is its distance past, or why don't we just say distance from natural length? Because it's both, it takes force both to push it smaller and to pull it longer. Okay, so every spring would have its own constant. I mean, some springs are really tight and it would take a lot of force to pull it or push it. Some, like a slinky, wouldn't take much at all, so the constant varies according to your spring. So we're told that a force of 10 pounds is required to hold a spring 4 inches stretched beyond its natural length. Okay, so a force of 10 pounds is required to pull it 4 inches, and 4 inches is 1/3 of a foot, beyond its natural length. So that little piece of information tells us that 30 is the K. Does everybody see what I did to get 30?
Mm-hmm.
We multiplied both sides by 3 to cancel the 1/3. So 30 is the K for this particular spring. Find the work required to stretch the spring 6 inches beyond its natural length. So what we want to do is we want to picture pulling it incrementally so that we're pulling it from its natural length, and then we incrementally are pulling it until it's 6 inches beyond its natural length. And as I do that, I'll be adding up incremental amounts of work. So my function that describes the force is 30 times x. Okay, 30 times x is the function that is describing my force for this particular problem. So force times distance, there's my definition of work. This is the force, this is representing the distance. Force times distance. And if it goes from its natural length to 6 inches, it will go from 0 to 1/2 of a foot. I'm rewriting things in terms of feet just so that the units match the standard units. Again, we could leave it in inches. Mathematically, it wouldn't be a wrong answer. You just would have to make sure that you put the correct units down. I mean, you'd have to list your answer in terms of inches instead of feet.
Should be inch pounds.
It would be inch pounds, yeah. Which again, there's nothing wrong with that. It's just not the standard. Mathematically, it's not wrong. It's just not the standard. So again, the area under this curve is equivalent to the work we're trying to find. So the fundamental theorem of calculus tells me I can take the antiderivative of this and plug in my limits. So the antiderivative of 30x is 15x squared. And so I get 15 times 1/4 minus 0. And what is that? 3.75, yeah. And I changed the inches to feet, so it's foot pounds. Right, so 3.75 foot pounds. Yes, Javon?
Can you explain why the upper limit is 1/2 again? I'm sorry.
In the problem, we're told find the work required to stretch the spring 6 inches
Okay,
beyond its
all right.
natural length.
Got it.
And just to keep the units the standard, I changed it to feet.
Okay.
Okay, number 3 is a twist on this type of problem. Not to have a fun with, but, okay, in the problem we're told that 6 joules of work are required to stretch a spring between 10 centimeters to 12 centimeters. and another 10 joules are needed to stretch it from 12 centimeters to 14 centimeters. So as you stretch it, it requires more force, is what we're basically, what we're basically learning here, okay? What is the natural length of the spring? Okay, so 6 joules of work are required to stretch it from 10 centimeters to 12 centimeters. And we're assuming that Hooke's law holds. I don't know what the spring constant is. I'm going to try to figure that out. But I do know that if I did know the spring constant, if I stretched it from, let's see, it was 10 centimeters, right? So we
Yeah.
want to change that to
0.1.
meters, wait, sorry, wait.
Yeah,
Yeah,
0.1.
10.1, yeah. And I don't know what the length is, but the reason why this was 0 was because we were stretching it from its natural length to something. And so if the, like for example, if the natural length is 10 centimeters, then this will be 0. It's just I don't know what the natural length is, and so all I know is that this low limit should be the difference between what the natural length is and I've stretched it to 10 centimeters, and then this would be 0.12 minus L. Okay, so just again to kind of help you understand these limits, if the natural length was 10 centimeters, then this would be 0, and its natural length is represented by 0. If its natural length was 10 centimeters, then we would have stretched it from its natural length to 2 extra centimeters, and this would be 0.02. But I don't know what its natural length is, so my low limit should be the 10 centimeters minus whatever the natural length is. My upper limit should be 12 centimeters minus whatever its natural length is. But I want to stick with the standard units of a Newton meter, so this is how I'm representing 12 centimeters. This is how I'm representing 10 centimeters. Okay, so working through that problem, I get kx squared over 2 evaluated between 0.1 minus L and 0.12 minus L is supposed to equal the number 6. And so K times 0.12 minus L squared over 2 minus K times 0.1 minus L squared over 2 is supposed to equal 6. Okay, see what I'm doing is I'm plugging my upper limit in for X, and it's creating this equation that I'm going to end up having to solve. Just to kind of clean it up, I'm going to multiply both sides by the 12. And then we're going to kind of leave this off to the side because technically I've got 2 variables. K is an unknown right now as well as the L. So in the problem, in terms of being a textbook problem, that's why they gave us that extra piece of information. If you were really doing this experiment, you'd have to somehow find some extra piece of information if you really were trying to solve. So the second piece of information is that 10 joules, so 10 joules of work were required to stretch it from 0.12 meters to 0.14 meters. And so we're going to get the same antiderivative. We will get a second equation. I'll just kind of write it over here so we have them together. So I'm plugging the upper limit in there, so I get 0.14 minus L squared over 2 minus 0.12 minus L squared over 2 Alright, so here are my two equations. And once I have two equations and I have two variables, I can simultaneously kind of solve them to figure out my variables. So, I don't know, those look a little messier than they need to be, so hang on, let me. Okay, from the top one, I'm taking the k times 0.12 minus L squared, and I'm separating it, okay, so I'm setting that equal to 12 plus k times 0.1 minus L squared. Okay, so the first one that I found, I solved it for the k times 0.12 minus L squared, and then I'm gonna do the same thing to the second one. But, hang on, sorry, I recopied and then if I do the same thing to the bottom one, I have to be a little careful here. If I subtract the one with the k 0.14 minus L squared, then the one with the 0.12 has the negative in it. So I'm going to flip those around. So I will have k times 0.14 minus L squared minus 20. Okay, I took both of those and I recognized that they both had that common term of the k times 0.12 minus L squared. And so I'm capitalizing on that, because then I could set those equal to each other and whittle down to at least one of the variables. So let's see. I'm trying to decide on my. Is it cleaner to solve for k first or well, I guess we multiply.
Yeah.
Yeah, it's
You have 'em.
easier to.
You foiled out both of them
Yeah,
to begin
yeah.
with.
Oh, did I
Yeah.
do that first?
Yeah,
I wonder if it makes a difference.
They're foiled out before you set them equal to each other.
Yeah. Oh.
Because one of them you get 12 equals k
Yeah.
times 0.0044
Yeah, I
minus
think it probably
0.00.
doesn't matter, but I don't think it, I think I did that when I was typing that up, but I don't think it matters.
Okay.
Because if we FOIL this out, then I'll show you why I can tell it doesn't matter. Hang on, what's 0.14 times 0.14? Is it 0.0196? Is that what?
Sure. 0.4 times 0.4.
0.0016.
Point
Oh,
zero-
sorry, 0.14?
Yeah, 0.14 times 0.14.
Yeah, you got it right. 0.0196.
Alright, and then plus L squared, and then minus 20. Alright, the reason why it didn't matter if I FOILed it out sooner or later is because this times this is on both sides of the equation,
Mm-hmm.
and so it gets canceled out whether I FOILed earlier or later. Okay, I mean, the K is not completely gone, I'm just pointing out that if you then distribute, you're gonna have a K times L squared on this side as well as on
Mhm.
that side.
I got you.
So then, we can at least. Equals 0.0196 K minus 0.28 KL minus 20. So then, if I out of both. Sorry, I factored K out of the terms that would have had the K in it, which I guess I didn't really need to do this step. Really, I kind of did just to indicate that we lose our KL squareds at least. And then, I'm gonna put, shoot, it seems like, if I add 20, then we're gonna have 32. I added the 20 over to there to get the constant on one side. Then 32 would equal 0.0196 K minus 0.28 KL minus 0.01 K plus 0.2 KL. I'm moving these two over here. Have 0.0096 K minus 0.08 KL. So then 0.0096 minus 0.08L. So 32 divided by 0.0096 minus 0.08L is K. And then we should be able to plug that back into one of our equations and come up with what we end up with for K.
10,000 is what it says.
Is what K is, okay. So then, I'm gonna, because I do wanna talk about one of the other problems in our last 5 minutes, okay? So, plug this back into it, really any one of the equations, I'd find the cleanest one and can solve for K, and I'll finish it off the way we had it finished off, okay? And our last, I mean, if we had 15 more minutes, I would work